Welcome to Lecture 12. We're off to sunny Italy. Thus far, we've spent a lot of time in England, France, and Germany. We've been to Sweden, been to Holland and Switzerland a few times. And in the last lecture, we got over to the American colonies with Benjamin Franklin's work in electricity. Later, we'll go to Denmark. But the story of Galvani and Volta, it's about something called animal electricity. That's an Italian story. We learned a lot in our last lecture about how the study of electricity took off in the 18th century. We saw that leading up to the century, natural philosophers had gathered a good deal of empirical information about how certain substances can be made to attract light objects like feathers to their surface. All you had to do was to rub them, and they would display this effect. Then came advances in instrumentation, thinking here of Hawksby's spinning glass globe. That enhanced the power of the effect. Eventually, they realized how to produce shocks and sparks. What they had learned was how to make substances acquire a static electrical charge. Finally, we followed the early electricians as they figured out how to make a portable sparking machine, the Leyden jar. It was a bewildering phenomenon, not only because of the circumstances surrounding its discovery, but even afterward. What was going on? Why did the same person who held the jar as it was being charged have to be the one to discharge it? These questions and more were answered in Ben Franklin's explanation of the jar. When the jar was charged, it was piling up the imponderable electrical fluid on the inside surface of the jar. And that caused the normal electrical fire on the outside of the jar to be driven into the ground. This produced a very unstable situation in which there was more than the normal amount of fluid inside the jar and less than the normal on the outside of the jar. And all that was needed was a route for the excess inside to get to the outside. And that's what happened when the same person holding on the outside touched the nail that led to the inside. Well, in this lecture, we'll take up a question that arose later in the century. And it will have to do with this Leyden jar, as we'll see. Do animals possess electricity? We'll see how this question arose in just a minute. But let me assure you that this subject was important in the history of electricity for a couple of reasons. First, it opened up a whole new area of research. We saw last time how natural philosophers had used the human body as a detector of the flow of electrical fluid. They knew that when electricity flowed through the body, it caused the muscles to contract. Georg Bose once rigged up a way to shock the guests around a dinner table to the delight and entertainment of everyone. So the body was known to react to electricity. But once it was suspected that it produced electricity, well, then there was a lot more to do than play parlor games. A reason why the subject of animal electricity was important was that it was the context for a major new discovery that no one anticipated. I'm referring here to the invention of the battery and the creation of current electricity. Electrical current was like a continuously discharging Leyden jar. This was phenomenal. Now there's even more to do and to explore. And the amazing thing was that it linked electricity to chemistry. The way to produce electrical current appeared to involve a chemical reaction. Things were getting curiouser and curiouser, as they say. Grist for the mill where the natural philosophers concerned. That's exactly the way natural philosophers like it. The more mysteries there are, the more there is to do. Animal electricity was also important because it linked electricity to life itself. That prospect was part of the reason why the initial announcement of an animal electricity created so much excitement. It caught the imagination of the public as well. We all know of Mary Shelley's story, Dr. Frankenstein, who uses electrical current to bring the monster to life. That was written in 1815, just 2 decades after the subject burst forth onto the European scene. It was a literary reflection of how public some of the new discoveries in natural science were becoming. Natural science was now helping to sell novels. Finally, this episode contains some lessons of a different kind. It helps us to see how natural science sometimes develops. This particular story uncovers some of nature's real complexity, but sometimes we don't want to let nature be complex. Sometimes we insist that nature is simpler than it is. We press nature into an either-or situation when it would be better to see things as a both-and. And when we make things into an either-or, it's easier, more tempting to declare winners and losers. But sometimes there's more than one winner. We're going to see an example of this in the controversy I'm about to describe. The first phase of the story centers around the work of the Italian Luigi Galvani. Galvani was a lecturer in anatomy at the University of Bologna and professor of obstetrics at the separate Institute of Arts and Sciences. He began doing experiments on the relationship between electricity and physiology in the late 1770s. That meant that he had acquired various forms of the new electrical machines that had by then appeared, ever more efficient arrangements to produce electrostatic discharge. He was in a medical field, and he was not alone in wondering what therapeutic value this newly harnessed force of nature might have. So he was experimenting. Along with his regular work in anatomy, which involved a lot of dissection of animals, he was applying electrical discharge to muscles so he could study the responses. As we've already noted in our discussion of this amazing field, electricity was always full of surprises. Another one occurred in Galvani's laboratory in September of 1786. An assistant of Galvani, most likely his wife, Lucia Galeazzi, noticed something very unusual. We're not absolutely sure it was his wife, but we know that Galvani himself was out of the room, and we also know that his wife often assisted him in the laboratory work, so scholars have assumed that it was she. Anyway, Lucia was amazed to observe that a dissected frog's leg convulsed violently when the tip of a scalpel accidentally touched a nerve. Why would that happen? And then she noticed that another assistant across the room was producing sparks with an electrical machine. Could that have played a role? Nah. But electrical sparks do cause contraction, but that's when we touch a muscle directly. Better go get Dr. Galvani. Well, Galvani was summoned, and they set about to test the idea that somehow the electrical machine was responsible for the contraction in the frog's leg. It would be easy enough to do. Try touching the scalpel when the machine is sparking and when it's not. Didn't take long to confirm that the initial suspicion was correct. Electricity discharged from a sparking machine could affect muscles even when not applied directly to them. Well, this was something new. Galvani continued his experiments on electricity and physiology with a vigor, and he didn't stop with the kind of electricity that humans could produce. He involved nature's electricity, lightning, as well. And once again, he came up with a mysterious result. Yet another one. First, Galvani ran an insulated wire from a prepared frog, which he placed in a glass jar in his laboratory, and ran the wire to the roof of his building. When a thunderstorm passed overhead, he was able to notice contractions in the frog's leg. Well, so far there's nothing all that surprising. We know that lightning is electricity, and so it should make the frog's leg contract. But then Galvani put some frog preparations on copper hooks and hung them on an iron trellis he had outside. During thunderstorms, he again noticed that the frog's legs would twitch. Again, not all that surprising. But then the surprise did come. Sometimes the frog's legs on the trellis would twitch even when the weather was fine. Now what's going on? Is there electricity in the atmosphere even when there's no lightning? Once his attention was drawn to this, Galvani found that he could make the contractions occur in the frog's leg himself just by pressing the copper hook against the iron trellis. So maybe this didn't have to do with the electricity in the atmosphere at all. We can just imagine him thinking to himself, just how complicated is this subject of electricity? Well, he took the frog inside, out of the weather, and put it on an iron plate. If he pressed the hook against the plate, the same contractions occurred as outside. So now he knew that the contractions he'd observed in the good weather weren't due to atmospheric electricity. And it was clearly not due to a sparking machine, since there was none being used when he brought the frog inside. Now all he had to do was to explain why the frog's leg was contracting, because it clearly did contract when he pressed the copper hook against the iron plate. Faced with this situation, a natural philosopher has to come up with an idea, a hypothesis, and Galvani did. He concluded that he discovered a new kind of electricity, a third kind, different in origin from the natural electricity in the atmosphere, the lightning, and from the artificially made electricity of the sparking machines that also were known to produce contractions in muscles. This new third kind of electricity was apparently stored in the muscles of animals. He called it animal electricity. Isn't it fascinating to realize that Galvani in Italy is coming up with animal electricity right around the same time that Mesmer in France is appealing to animal magnetism to explain disease? Well, be that as it may, in fact, Galvani concluded that animal muscle must be able to store electricity just like a Leyden jar does. He thought of muscle tissues as having their own Leyden jar in them, so to speak, all set to be discharged if a route could be found to let the excess electrical fluid inside get to the outside of the jar. In this case, he imagined that the internal parts of muscles contained the excess of electrical fluid, while on the outside of the muscle there was a corresponding deficiency. He assumed that while the animal was alive, this imbalance could be created in the body's muscles by the brain. The brain could also cause the discharge of the imbalance. That's how the brain regulated muscular movement. It created an imbalance when it then discharged, which it then discharged to produce contractions whenever they were needed. Ingenious thinking. He referred to one more thing. The brain accomplished its regulation by means of the nerves, which connected the inside of the muscles to their outside surface. Galvani acknowledged that the common wisdom was that the nerves carried a nervous fluid in the course of doing the brain's bidding, but he said, I'm now going over to the side of those who've been saying that the nervous fluid is really electrical fluid. He suggested that the outer sheath of the nerves was there for a reason. It insulated the fluid flowing inside the nerves from contact with the muscle as it flowed from the inside to the outside. Of course, when he was doing the frog's leg experiment, there was no brain present to cause the discharge, so Galvani had to provide an artificial means of discharging the muscular Leyden jar. He had to bring the inside of the muscle in contact with the outside so the muscular jar could be discharged. To do this, he established a metal contact with the nerve, which ran to the inside of the muscle, and then attached another metal lead to the outside of the muscle. Now all he had to do was to bring the two metal leads into contact, and voila, a route from the inside to the outside was created. The excess fluid inside can then flow to the outside and cause a contraction in the process. And that's exactly what he'd done when he pressed the copper hook against the iron plate to produce the contraction. This is a well thought out theory. Pretty impressive stuff. And that's exactly how Galvani's announcement of his work was received, as a truly amazing discovery. When Galvani made his discovery of animal electricity known in a publication of 1791, it was regarded by many as nothing short of path-breaking. Listen to this judgment, which was a professor of anatomy in Mainz, who wrote that Galvani's discovery, and I quote, supersedes by far in importance everything which has been thought and written about natural science since the time of Aristotle. Wow! Since the time of Aristotle? That's going back some. And think of what Galvani's discovery is supposed to have outdone. Copernicus, Galileo, Newton. This professor is saying that the link between electricity and life that Galvani has uncovered is more significant than the reordering of humankind's position at the center of the cosmos that came about as the result of astronomers of the 16th and 17th centuries. Well, among those who were impressed by Galvani's achievement was his countryman, Alessandro Volta, who was a professor of natural philosophy at the University of Pavia. Volta not only agreed that it was an important discovery, he agreed that Galvani was right in his analysis. Well, he agreed initially with Galvani's conclusions. But Volta was someone who had his own history with electricity, and he didn't come at it from the viewpoint of an anatomist, so it wasn't too long before Volta began to waver in his agreement with his fellow Italian natural philosopher. Volta worked primarily in physics. He had done a lot of experiments on electricity and was very familiar with the latest electrical machines. In addition, he was aware of work that others had done with metals, and that intrigued him as he thought about the fact that in Galvani's experiments, copper had been brought into contact with iron. Volta knew of experiments that had been done in which two metals were brought into contact with each other and which also involved the animal body. Again, just like Galvani's frog experiments. But the body in these experiments was not a frog, it was the human body. See, natural philosophers, being the curious folks they are, would often do experiments on themselves. Even Franklin had in his kite experiment. Well, Volta knew about experiments in which two metals had been touched together at the same time both metals were placed in contact with the tongue. You can visualize this arrangement if you think of pinching the tip of the tongue between two metals, making sure that the ends of the metals outside the mouth are in contact. What was reported in these experiments was that the person experienced a bitter taste. But the folks didn't stop there. They ran a lead, some of them, to the eye from this arrangement to see whether the sense of sight could be stimulated as the sense of taste had. Sure enough, in that case, you saw flashes of light. As he thought about these experiments, Volta began to wonder, maybe that was what was going on in Galvani's case. Maybe it wasn't what Galvani thought. Maybe the contact between the copper hook and the iron plate was the source of the contraction by whatever caused the bitter taste and flashes of light. After all, if taste and sight were affected, the contraction of the muscle could be a response to the sense of touch being stimulated. In fact, Volta didn't doubt that electricity was involved in Galvani's experiment. He just wanted to consider if possibly contact between two metals might be a source for an electrical discharge. In that case, Galvani's assumption that the metal leads acted merely as conductors of electricity might be wrong. They might be the source of the electricity. So he began his own set of experiments to test out the idea. He would try contact between different metals and see. The more he got involved in the work, the more he became convinced. And of course, he didn't keep his views to himself. He began to suggest publicly that Galvani was wrong. Now, Galvani died in 1798, but his nephew, Giovanni Aldini, became his staunch defender. And soon there was a heated controversy between Aldini and Volta, an internal Italian fight about the source of electricity in Galvani's experiment. In this connection, the word galvanism began to be used as a synonym for Galvani's animal electricity. Then, in a letter written on March 20th, 1800, to Sir Joseph Banks, who was the president of the Royal Society in London, Volta announced that he had made a new invention. It had come out of his experimental work on electricity and contact between metals. It soon became known as Volta's pile. It's what we call the battery. Volta compared his discovery to the Leyden jar, and it was like the Leyden jar because it produced electrical discharge. In the case of Volta's battery, however, the discharge was very weak. That was the bad news. But the good news was that the pile didn't produce a discharge that occurred and then was gone. The discharge kept on discharging. It was like a continuous electrical discharge, a continuously flowing current of electricity. How had he done it? How had he pulled this off? Well, he imitated the arrangement of the metals in contact on the tongue. Remember, there, two metals were brought into contact while both were in contact with the tongue. So Volta assumed that nothing about this was accidental. Metals had to touch each other, and both had to touch the animal part, in this case, the tongue. Further, he assumed that the tongue was not accidental either. Whatever was to be the medium that both metals touched had to function as the tongue had in the earlier experiments. So he brought zinc and silver into contact with each other, and then made sure both the silver and the zinc were in contact with a medium. In the other experiments, when the tongue was involved, you could feel the result in the taste produced. So Volta used his whole body in place of the tongue. He connected leads to the two metals, which he held in his hands. In this case, he would become part of the circuit, just as the tongue had been earlier. If he did this with the arrangement I just described, the effect was extremely weak. So he decided he would have to increase it. He magnified the effect by piling up sets of silver and zinc discs in contact, silver on top, zinc beneath. Each set separated by a paper soaked in a brine solution. Now he connects leads from the silver at the very top to the zinc at the very bottom of the pile. If he held these in his hands, he could feel that the discharge was much stronger. Volta had shown that two metals in contact could, under the right conditions, produce a strong electric current. It was a milestone of scientific discovery. Now, of course, this discovery was celebrated for what it was, a breakthrough that would open up to the field more investigation and experimentation. Imagine what might now be possible. The whole thing had come about as the result of considering the interaction among metals, but that was traditionally the chemist's preserve, so the discovery linked electricity and chemistry together in a way that was new. And that opened the door to new experiments in chemistry. Did the chemists respond? You bet. Before the year was out, chemists had run electrical current through water and demonstrated that it dissociated into two gases, hydrogen and oxygen. A liquid was made up of two gases. Amazing. And that was just the beginning. A whole new field of electrochemistry was born, and soon electroplating was happening and all kinds of other things. Think about what the discovery of electrical current might mean for other fields. Medicine. Could it be used to help alleviate pain? Did it have any healing properties? Could it be used in other ways to treat patients? And physics itself. How might we tap the continuous action of this force? And what is the relation of electrical force to nature's other forces? This last question in particular will be a central concern for us in Lecture 25. For example, wires got hot when current ran through them. Clearly there was a relationship to heat. What about light? And a really interesting question, what about mechanical force? Can electrical force be used to move matter? So Volta had done something important in his theorizing about electricity and metals and in his invention of the battery. And there were some who concluded that he had, in the process, proven Galvani was wrong. His eventual fame helped that impression along among historians who later looked back on this whole episode. But historians are human. They have sometimes allowed their wish to celebrate scientific heroes to distort the historical record. I think this is a case in point. Volta's discovery has in the past been cast as a correction of Galvani's theory of animal electricity. And I think you can see why some have had that impression. From what we've learned so far, it does look like Volta has explained what was going on when Galvani pressed that copper hook with the frog's leg on it into contact with the iron trellis. The iron-copper contact, with both touching the moist frog's leg, produced a flow of electricity that caused the frog's leg to twitch. It was not that the tissue contained muscular light in jars, as Galvani said. That was indeed an ingenious theory, but Volta's makes a lot more sense. And it's a lot simpler, and frankly, a little bit easier to believe. Besides, what about all those experiments that Volta did? Don't they prove that he was right and Galvani was wrong? Well, I'm hardly going to deny that the invention of the battery did confirm Volta's view that contact between metals can produce electrical current. But does this mean that Volta has shown that contact between metals was the only source of electrical discharge in Galvani's earlier experiments? That's what some historians have implied. And when they've seen things this way, they've cast Volta as the winner in the debate over animal electricity. I suppose this is understandable. We like stories where there's a winner and a loser. That's one of the great attractions of sports. On a Saturday afternoon, you can settle things one way or the other. That's why people hate tie scores, because there it didn't work. We see the same temptation in politics. What will be the best soundbite on a given issue? Never mind that the issue is complex, that there's no easy solution. We don't like messy things like that. It's just too hard to deal with. And sometimes we don't like our history messy either. Take this question that divided Volta and Galvani. Did Volta's demonstration that electricity can be produced from contact of metals prove Galvani's idea of animal electricity was wrong? I don't think so. I don't think that was necessarily entailed. It was still an open question. And what's really interesting is that the invention of the battery was not decisive here. It was not regarded at the time, even by Volta himself, as the deciding factor in his disagreements with Galvani. Volta's disagreement with Galvani was already in place before he invented the battery. At the time, the pile was seen as an amplified form of galvanism, which, for many, occurred in both metals and animals. During these years, including the years right after the battery was invented, investigators were dealing with two possible sources of electricity that produced the contraction in muscle tissue. One was due to contact between two different metals, just as Volta argued. But the other was due to electricity that's stored in the muscles, as Galvani said. The German investigator Alexander von Humboldt, for example, did an experiment during the time of the controversy that made it clear to him that things weren't as simple as Volta said. He used leads that were suitably attached to a prepared frog's leg and then lowered the leg very carefully and slowly into a preparation of silver. Connecting the leads, he was able to show that the leg contracted. Von Humboldt was here using only one metal, and he produced a contraction in the frog's leg. So he knew that Volta's assertion that Galvani was wrong, that the contraction was not due to electricity in the tissue itself, but to the contact between two metals, wasn't completely correct. He'd done it using only one metal. As we've already seen on more than one occasion, the development of science frequently demands that investigators make sense of a host of conflicting information. The new science of electricity certainly has illustrated this. From the very early days when natural philosophers were learning how to make substances display the electrical attractive force, right on up to the mysteries surrounding the interaction between electricity and animal tissue, investigators have been confronted with results that bewildered them. We know that eventually investigators are generally able to focus on central clues and identify the minor contradictions as of lesser importance. This is how they put things together into a coherent account that convinces the majority, at least for a while. One of history's lessons is that before the fact, before the consensus is constructed, it can be virtually impossible to identify future winners and losers. Sometimes what appear to be outlandish ideas turn out to have a staying power for reasons that nobody anticipated. In the case of the Leyden jar, it was hard for people to realize that the same person had to hold the flask who touched the nail at its top. That's a crazy idea. Why did that have to be? Only with time did the reason become clear. The more open natural philosophers were to so-called crazy ideas, the more rewarding things could be. But what then about the real crazies? We know that history has had its share of crackpots too. Before the fact, how do you tell the difference? The point is, you can't, not with certainty. But natural philosophers, and historians too, have always been human. They sometimes, not always to be sure, but sometimes succumb to the temptation to decide too quickly who the good guys are. And if, here at the end of our exploration of science in the Enlightenment, you think we've seen this confirmed, it won't suddenly stop as we keep going on into the 19th century. In many ways, this situation will only become more evident in the new century. And we'll begin our exploration of the amazing 19th century in our next lecture.